So, in yesterday's lecture, we went over how if you have an object, right, like a mass that's attached to a spring, and for instance, you displace this mass, you know, a little bit by like a delta x, and then you let go of it, that it'll oscillate back and forth. And this exhibits what we call simple harmonic motion, right? Okay. And simple harmonic motion can be written as an equation, like the position can be written as something as this. Usually it's like x of t is equal to some amplitude, and then we see cosine omega t, and then plus phi, but like phi is usually 0. Like usually we don't really put like a phasing on things. So a cosine omega t is usually what we have. Okay. You might notice something cool here because a cosine omega t, right, looks like, let's say for instance, like r cosine theta, right? And you might remember from your you know, high school math days that r cosine theta is something special, and it's the parameterization of the x coordinate of something in polar coordinates. So, for instance, if you had a circle as, well, that's a square. A circle. Nothing against squares, but and for instance, you wanted to look at let's say something at like, which has like a radius r, right? Or here, let's tone that down. A radius r, and then an angle theta, right? Then the x component of this, right? So the x, the coordinate of this thing in x, this would be equal to r cosine theta. Okay. So it so happens, right, in the same way that the position of something one second, let me get rid of this. There you go. Will look like a cosine omega t, right, as it oscillates, you know, forwards and backwards from like some equilibrium point. If you were to, for instance, take a point on a circle and then rotate it around at some, you know, theta that keeps changing, the x coordinate would also look like simple harmonic motion, which is really cool. I think how we usually do this is there's a picture for this. Let me think. So harmonic motion circle animation. I'm sure someone's done one at some point. Let's see. Yeah. Oh, this is always very cool, but I want it in like, you know what? Someone's done it on Manum. I know they've done it in Manum. Harmonic motion Manum. Yeah. Well, sometimes like a video of it on like YouTube or something. Oh, the pre-lecture? Oh, it did? Oh, nice. Oh, you were talking about like in the video. Oh, that's good. Actually, yeah, let's go check that out. Yeah, real quick. Yeah, no, I appreciate that. All right, cool. Yeah, I was looking for it. I was like, I've seen this done so many times. What happens to the modeling of a simple harmonic motion if it's done with an oblique? Well, that's interesting. If it was oblique, then you would have it spending like more time in certain at the endpoints, I guess, right? Yeah, they probably have some. Well, this is fluids actually. Sorry, my bad. Oh, and I hit back. Never hit back. See, even I like make that mistake sometimes. Periodic. Oh, also, yeah, we're gonna go over the clickers. I just released clickers for today as well. All right, let's see. They probably have a graph here somewhere. We got like a video of it. Yeah, there you go. Cool. Where's the thing that describes it as a circle, though? I want to see the circle. Yes, here we go. Great. Ooh, nice. Cool. Yes, this is a perfect animation. I love this. Yeah. Good job. Yeah. So, right, as something is moving around in a circle, the x coordinate of it also looks like simple harmonic motion, which is like, yeah, sine and cosine stuff. Very cool. Yeah, if something was an ellipse, then it would spend more time at the endpoints, and that's kind of weird. We're going to go into like damped oscillators and driven oscillators because those are some other cases where the motion looks a little funny. It's not going to look like as circular. Okay. So let's see. All right, so we went over circular motion, or sorry, simple harmonic motion looking like circular motion. Right, yeah. Oh, this is the big diagram they have. They do something with the lights. That's cute. They say like the shadow. Let's see. Yeah. I guess, right, if you were to like shine lights on something, then the shadow that something makes would be its x-coordinate, right? Do you see how that works? That's actually kind of cool. That's a decent explanation for it, I guess. Yeah. Right, if this is here, then you're going to create a shadow here, and that's the x-coordinate. Okay, cool. Yeah, it looks the same. And then from that, you can also get some intuition about the velocity, for instance. Because, yes, the angle, right, would be equal to the angular velocity times the time, omega t. So the comparison here was, right, instead of doing, like, theta, you have theta is equal to omega t. And that actually kind of looks the same thing, right? X is equal to velocity times time. Theta is equal to omega times time. It's just the angular component of it. If you were to take a derivative, then that would kind of that would show like the instantaneous velocity, which would would be tangent to it. Very cool. Okay. Let's get to the next thing, which are pendulums. Pendulums are really cool. Okay. So here we have, for instance, the force diagram on a pendulum. Because pendulums also exhibit simple harmonic motion, right? You've ever seen it before, right? If you like pull something up and it like swings back and forth, that also is simple harmonic motion. And we can derive where that comes from in a similar way that we did for springs by first drawing a force diagram. So you may remember this from last quarter, or if you took 1A last quarter. You have mg pointing down, you have tension pointing up, and then what we can do, similar to what we did on an inclined plane, is you can break up this mg into components that are tangent to its motion and also normal or like perpendicular to its motion. Okay? So this thing will move in this direction. This minus mg cosine theta, right? That's always going to be equal to the tension in the rope. And then you're going to have this minus mg sine theta. This is the restoring force. So it's interesting. We don't need to do energy conservation here. I'm going to show you how it works. We actually can use just like differential equations. But it does apply as well. You also have conservation of, in this case, right, the spring potential energy is gravity. So in previous examples, right, when this thing, compressed or like stretched out and like stored energy, that was in like a spring. Here it's being stored in gravity, which is also linear, right? Because energy due to gravity is mgh, right? Which is cool. But the main thing here is also that the linear, sorry, not is that the restoring force is linear, okay? For small angles. There's an approximation here for this to happen. So remember that simple harmonic motion only occurs when you have a linear restoring force. So when you have the force that is trying to bring you back to equilibrium is linear, and we say like linear with respect to distance away from equilibrium. Okay, so with the spring, for instance, that restoring force was equal to negative kx, okay? Here, with the pendulum, that restoring force is equal to negative mg sine theta. Okay. Now you may be, a little confused here. being like, wait a minute, Dr. G. Like, sine theta is not linear. And you'd be correct. I mean, yeah, sine theta is technically sinusoidal, which means, it oscillates. However, there's an approximation we make. It's called the small angle approximation. We've done it a couple times, I think, already in this quarter, and we're going to do it forever in physics. So for small theta, which they say if theta is less than 15 degrees, you can approximate the sine of theta as just equal to theta. So in this case, the displacement that it is like linear. Yeah. Okay. But the derivation for how this works, so when we did a spring, right, we did sum of forces was equal to mass times acceleration. In this situation, we're going to do the sum of torques is equal to I alpha, right? So let's remember, again, from mechanics, that if you have the sum of the torques on an object, torques are like the forces that want to rotate things, that has to be equal to I times alpha. This is the analog to F equals ma, right? Instead of torque, it's force. Instead of moment of inertia, it's just mass. Okay. But in this case, the torques acting on this thing, right, is going to be equal. Well, there's only one torque, right? Let's also remember that torque is technically equal to R cross F, which is really the same thing as like R F perp. So the amount of force perpendicular to the radius. So looking at our pendulum here, the force, why can't you use the derivation using F equals ma? Because the acceleration is kind of changing. It's because it's moving in a circular motion. The oscillation, right? The simple harmonic oscillation that we have is in terms of like the angle. It's in terms of theta, right? If we were to like see a graph that looks like this would be measuring the angle theta. It wouldn't be measuring like the angle x or something. So because the simple harmonic motion is, we say, like parameterized in the, polar coordinates here, right? Like r theta describes like the, position per se of this thing. That's why we want to do things in angular terms. With the spring, you had things moving in the Cartesian system, which means they were just moving to the left and to the right. And so simple harmonic motion could just be referring to x. Here, some simple harmonic motion refers to the angle theta. Okay. Because I'm pretty sure like the other things they're not like exactly simple harmonic motion. Like the height, right? The height's going to change and stuff. Yeah, it's all about like you want to put things in a coordinate system that makes sense. This is a thing you'll do outside of this class in future physics classes, is picking like a reference frame and like picking a coordinate system that makes sense to what you're doing. We're trying to describe simple harmonic motion of the angle, so we want to talk about forces in like the angular directions and motion in the angular directions. And in that case, that involves using torque. So sum of torques is I alpha. That means that I alpha is going to equal my torque, which there is only one torque on this thing, right? And it's this. This is going to be negative mg sine theta times L. Okay? Right? So then what I can do is I can recognize that, oh, okay. So alpha, if we remember from kinematics, right? So omega is d theta dt. Alpha is d omega dt. These, again, the same analogs of position, velocity, acceleration. So this is the derivative of this, which is the derivative of this. So it's the second derivative of theta. So you have I d squared theta dt is equal to negative mg L sine theta. Okay. And then what I'm going to do, right, I'm going to divide both sides by I. And so we're left with this. Cool. And this almost looks like my wave equation, right? Remember our wave equation, right? D squared x d squared x dt squared was equal to omega x, right? Omega squared x, sorry. Omega squared x. Right. Omega squared is k over m. Except that, like, this is now, like, the omega. But it would be nice if this was just theta. This is where we make the small angle approximation. We say that for angles that are less than 15 degrees, sine of theta and theta differ by less than 1%. And 1% is insignificant, right? Unless we're talking about the top 1%, then that's pretty significant. But, okay, so if we pull up our calculator here, I can prove it to you if you want to see. Make sure we are in this case, we're using degrees, right? Because, so, yeah, what, like sine of 15, or sorry, no, I want, I want things to be in radians. Sorry, my bad. Okay. So 15 degrees would be 15 times pi over 180. And you see how I get that gets you like 0.26. And then if I want 15 degrees in just straight radians, I get 0.26. So yeah, that's off by like what? Less than, it's basically 0.01. So it's less than 1%. So yeah. Now we can say that, okay, cool. I'm just going to say, well, sine of theta is basically equal to theta. For theta is less than 15 degrees, which is really, yeah, it's 15 over 180 pi. Can you explain how you went to the second derivative of x in terms of t? Yeah, so sorry. So this is not exactly this. I'm just showing that this was for springs. I'm going to say this is just similar. If you're talking about how I went from alpha to the second derivative of theta, that came from this. So if alpha is equal to d omega dt, that's equal to d dt of d theta dt. Here, let me put different colors for you. Okay, the alpha part, then yeah, don't worry about the x part. I'm just showing that this, which for springs, looks very similar for pendulums. Yeah, it's not actually equal to it. That's why I put the squiggly. It's like, it looks like it. It's like approximately kind of the same thing. Because, watch, because now I have d squared theta dt squared is equal to, oh, and this was negative omega squared x, sorry. Yeah, always forget the minus signs. Or don't forget the minus signs, but it happens. This is equal to negative, and then this is going to be mgl over I, right? And then this is going to be theta. This looks the same as this, and thus we can say that omega squared is equal to mgl over I, all right? So that is the angular frequency of oscillations of a pendulum, which for a pendulum, right, I is equal to ml squared. We say for a pendulum. So plugging that in, you get mgl over ml squared. M's cancel. One of the L's cancel. And you get G over L. And this is a very common thing, well known that you should know, which is that omega is equal to the square root of G over L for a simple pendulum. Yeah. This right here, this equation here, This is called the small oscillations. How did you get from the omega part from the second order derivative? So I did it by comparison. All right. It turns out. Sorry, can you explain the alpha? Okay. So okay, let me explain. Okay, alpha is angular acceleration, and then I alpha is torque. We understand that. And then similar to what we in linear. Let me put like let me do things like in pink isn't like linear. So linear, you had x, right? And then you had that v was equal to dx dt, and that a was equal to dv dt, right? And then in I say like angular motion, you have theta representing like position, and then omega is d theta dt, and then alpha is d omega dt. Okay. So alpha equals d dt of omega, which the derivative of the derivative is the second derivative with respect to time. Okay. So that's how I know alpha is d theta squared dt squared. And so when doing this, so I alpha, right? Sum of torques, I alpha. And that's also equal to R F perp. Or here we're going to say F perp times R, because then this is your radius, and then this is your perpendicular force that's acting on the pendulum. And then when you go down, like, so sub in alpha, you sub in this, move the I over, you get to this. This looks very similar to what we had for our equation, our differential equation for springs, which was the second derivative of x was equal to negative omega squared times the 0th derivative, or just the regular x. Here we have the second derivative of theta times some other stuff, right? Times theta. How do we calculate the moment of inertia? So we did that in mechanics, technically. I don't think we're going to go over calculating moment of inertia in this class. But in general, you should know that for a pendulum, it's 1/2 mr squared. Or sorry, it's just mr squared. There's a whole table of these. You're welcome, Sib. So, yeah, do you see how I did the comparison? Yeah, right? Yeah. We do this a lot in physics, actually, guys, is we do things for one, for one system, and then we say, hey, man, that looks pretty close to, like, some other stuff, so other stuff must be true. But these are the common moments of inertia that you would get. It's actually interesting. For a pendulum, it comes from the rod. How does this work? Yeah. Let me see. And I think you have to do the it's the parallel axis theorem is what you have to do. Yeah, okay, good. All right, you've done it 1A, yeah. Just because we have limited time, I can't go through everything. But yeah, if you want to know about the moment of inertia for a pendulum, there are derivations for it. I'm sure you can find it. For now, it's just ML squared is what it is. But okay, cool. Good question though. I mean, thanks. Yeah, I appreciate every time you. It's always good to know like where people are at and what people know and what people don't know. That helps me understand like where you guys are at. But yeah, cool. So we get that for a simple pendulum, and then if you do your whole omega equals 2 pi f, and then f is equal to 1 over t, you can then show that the period. So the amount of time it takes for a pendulum to oscillate once, like to go back and forth, is going to be 2 pi square root of L over G. Okay? And then what's good is to like look at this and be like, is this intuitive? Does this make sense in the real world? So, for instance, the time it takes for a pendulum to swing back and forth. If the length of that pendulum was more, right, it should take more time, right? Because the pendulum's got to like travel a lot. Oh, the assumption is the rod is massless? Oh, okay. Oh, you're right. It's just a point mass. Yeah, yes. Oh, yeah, it's just mr squared. I got you. Yes. Yeah, sorry, yeah, it's not a rod. Yeah, thank you. Fedekai has a good point here. Yeah, we just assume that this, for a point mass, yeah, sorry. That's totally correct. So point mass I is just equal to mr squared. So in this case, yeah, you don't, very good point, Fedekai. We assume that the mass of the string or the rod that's like holding that mass up is basically 0. But you could also find it if it was a non-massless rod. Like let's say, for instance, instead of having just a string attached to a mass, you had you know, like a rectangular thing that was like spinning around. This would have a moment of inertia, and that you would have to do the you'd have to do this. It would be 1/3 ml squared is what it would be. Yeah. Cool. Yeah, I forgot that like doing this pendulum, the pendulum is just a string and a mass for the simple case. It could also be a rod, but if the rod has mass, then you would need to replace this I with this. Yeah, and you'd have to add them up. Yeah, totally. Okay, cool. Good. All right. But yeah, intuitively, let's see if this makes sense, right? So for a simple pendulum, right, the period depends on the length. If the length is longer, it takes more time for it to go back and forth. And if gravity was more intense, right, if the force of gravity pulling you down was harder, then that would be a big number on the bottom, which would decrease the value of this, right? And so then the thing would oscillate faster and like not take as much time in between the maximum and minimums. Yeah. Okay. Cool. That's the pendulum. All right. They have then like physical pendulum. Cool. They go into like different eyes and stuff. Torsional pendulum. I don't think we're really going to touch torsional pendulums. I never really see that. Okay. What is important though here, right? Yeah, is damped oscillations, because damped oscillations represent like what the real world is. Okay. So here's an example of like what a damped oscillation, because when things oscillate, right? I think someone asked about this during last lecture, like what happens if there's friction on the spring and stuff. So is the period 2 pi squared of m over k, that's for a spring and that's for a pendulum? Correct. Yes. So actually, cool thing, Cameron, here that we should notice, and I forgot to mention this, is that for a pendulum, the mass does not matter, right? This thing is independent of the mass. So the amount of time it takes for things to swing is independent of the mass. However, right, yes, for a spring with a mass, now the period does depend on the mass, right? This was for a pendulum, and then, yeah, for a spring, omega is equal to, square root of k over m. So then period is equal to 2 pi square root of m over k. Yeah. Does the mass not matter due to reactive forces? That's a good question. I actually don't know why. I mean, I know the mass term just comes out because of... It's because the force is dependent on the mass. And then also, like, because the force is dependent on the mass, that cancels out, like, the mass term of, like, the MA part, right? When you're doing for a spring, let's remember that the restoring force, right, is independent of the mass, right? This is Kx. The restoring force does not care about the mass. So that will not cancel out ma when we do like F equals ma. Yeah. So it's cool. So if your restoring force depends on mass, then your omega and your period are independent of mass. But yeah, for the spring, you know why it's kind of cool is that for a pendulum, like the mass term, this is kind of like the mass. This is what we call like rotational mass because it's inertia, and inertia in this case, right, is very dependent on like how far away you are from your rotation point. So this is like, I would call this like rotational mass almost. Right, because you have I is equal to like ml squared, and right, this is the kind of the. I like to think of inertia as like rotational mass. Just the way I have of explaining it. Okay. All right, let's say, for instance, you have your mass on a spring. I think on a pendulum, it's that the tension increases as well as with mass, as long as the spring does not deform, the spring force should increase as well. Oh, okay. Yeah, okay. Okay, so wait, moving forward. So if you have a spring here attached to a mass and you had it oscillating back and forth, right? That would exhibit just free oscillations, right? And the amplitude would like go on forever. However, we do have what are called like dampening forces that kind of like steal energy away from the system. And in doing so, they start reducing the amplitude of something oscillating. So here, for instance, they have our mass on a spring, but now it's being submerged in a fluid, which has like some viscosity. And we'll note here, right, that if something is moving through a fluid, that it must exhibit some sort of like drag force, like some resistance. In the same way that like when a car is going down the highway, right, the air or the fluid that it's trying to like go through, that starts creating resistance and like a drag force that doesn't enable you to move as quickly anymore. And so, in the same reason here, the mass going up and down, moving through a fluid, that's going to cause a drag force, which is going to oppose the restoring force. So as this thing is like trying to be brought back up by the spring, you have drag forces trying to like keep it down. Yeah. So, and those drag forces are usually dependent on the velocity, okay? So when we write out our sum of forces for a situation like here, okay, instead of having just like ma is equal to negative kx, we're also going to have a minus bv here. Okay. Okay, cool. So now if we write this out as a differential equation, and we remember, right, that v is equal to dx dt, you then get this. So all we did is we moved this stuff over to the side, substituted in dx dt for v, and now we have this. If you've taken diff eq yet, you would know that there's an easy way to solve for this. And usually what it is you say like, right, say x is like e to the at, I think is what it is, right? So then like dx dt is equal to e to the, or is equal to a e to the at, and then d squared x dt squared is equal to a squared e to the at. And then when you sub that in for all this, you can then like cancel all the e to the at's, and you end up getting like ma squared plus ba plus k equals 0, and then this is a quadratic. Yeah. I'm not going to expect you to do this. You may do it in discussion, but and if you want, ask me during office hours. I'll do this derivation. It's pretty cool. But what ends up happening is that you figure out that the solution x, again, this is with Diffie Q magic, is equal to this. I would love to go through it. We just don't have enough time in 6 weeks for me to also cover all the math involved here. But again, I'm happy to explain it during office hours. Please come during office hours if you want me to do the math for you. So you end up getting that this is equal to your equation of motion. So that's the x that satisfies this differential equation. And what you notice here, right, is that I have my regular cosine omega t. No office hours today, no, because I have to get on a plane right after this flight. That's why this lecture is an hour and a half earlier. Yeah. But Monday I will have office hours, yeah. So, if this thing was gone, then it would look like the regular sinusoidal, right, harmonic motion. However, there is this e to the negative b over 2mt. This e to the negative t means that as time goes up, this whole thing will go down, right? Because e to the minus t is the same thing as 1 over e to the t. So as this gets bigger, you're dividing by a bigger number, which means you're getting a smaller number, which means you're eventually reducing this thing down to 0. And that's what we see here, right? Is that this oscillation looks like a regular cosine omega t, right? This looks like, cosine omega t, like cool, man. But then also the amplitude of it is decreasing. And that right there is the a e to the negative b over, or e to the negative b over 2m times t. So that amplitude decreasing is because of this term. Okay. Now solving for omega, in order to satisfy this, is not as simple. Again, I will do it during office hours if you want. It's a fun derivation. But you end up finding that omega is equal to this. So this is the frequency of your oscillations. And we should note, this is something cool, right? You remember how for a regular spring, that omega was equal to the square root of k over m, right? Or so omega squared was equal to k over m. We end up replacing this k over m with omega naught squared, such that now my equation is just this. And you're probably seeing a lot of letters here and you're like, wait, what's going on? Let's remember, right, that B here was because of this drag force. So if B was 0, if you had no drag force on this, and this oscillation was not damped, then you would just get this term going away, and you would just get omega equals omega naught. Yeah, so this is called like the resonance frequency. Or I think they call it the natural frequency. Sorry, they call it the natural frequency. And then this is the damping that causes like weird things to happen. Okay. And so yeah, you can then okay. So then there's a couple cases here, right? Because we notice that depending on what B is, this omega will do some weird stuff, right? So for instance, if this term ends up canceling out this term, you get omega is equal to 0, right? And then if this term is any bigger, then you get omega, then you get the square root of a negative number, and this becomes imaginary, which is like bad. So yeah, there's some cool stuff here, right? So we have a couple cases here. So we have if this b over 2m squared is equal to omega naught, you have a special case here, which is called, let me see, I gotta make sure I get this one right. Right, okay. This is what we call critically damped. And then if b over 2m squared is bigger than omega naught squared, and you have overdamped. Good. So yes. So Sib, omega is like the effective angular frequency of the oscillations. Omega naught is what the angular is what the angular frequency would be if there was no damping. Good. Yeah. So watch what happens. Yeah, it's overdamped. Exactly. And we're going to get into that. So it does move. It does move. It just doesn't oscillate. So watch what happens. So critically damped, overdamped, and if B squared over 2m or B over 2m squared is less than omega naught, then you have underdamped. Yeah, if there's no damping, then it is omega naught. Yes, correct. Right, and you can see here, right? If I have no damping, if B is 0, then omega just equals omega naught. Okay, so it turns out these are we can make like graphs of what this looks like, the different damping. Okay, and this is what we get. Okay, so this right here, right? This is overdamped. Or let me use the right colors. Sorry, let me use the right colors. Well, this is kind of like an aqua. How the hell am I going to get aqua? Oh, that looks pretty good. Right? No, a little too. We need more aqua. Okay, this is overdamped. The red one, this is critically damped. And then the blue one here is going to be underdamped. So there's a cool thing about critically damped, all right? Critically damped is the fastest way to get X to go to 0, okay? So if something is underdamped, right? It's going to keep oscillating back and forth, and it'll get less and less and less and less, but it's going to take some time, right, to eventually get to 0. Whereas if something is critically damped, that damping is so much that it causes it instantly to just go to flat, right? And it just stops. However, if you try to dampen something too much, such that it's overdamped, it actually takes longer for it to get to 0. And kind of like the cool metaphor, I think they talk about this, right? Because this is kind of weird. You're like, wait, why is critically damped go to 0 quicker than overdamped? Shouldn't more damping like make it stop sooner? Well, it so happens that if you damp something so much, then it basically has like friction that it can't even like get to 0. So imagine, right, you have a door. Like a door that's like swinging back and forth, right? If there's a little bit of friction, right, that's like an underdamped case. When you try to close the door, it'll go past equilibrium and it'll keep going back and forth a little bit, and then it'll like kind of stop. Now let's start ratcheting up the friction, such that now you get to a critically damped case, so that you go to shut the door, and it just does one oscillation and it stops. Okay, that would be something stopping the quickest. Now imagine you put a ton of friction on the door, or you make the door really heavy, right? So that it's overdamped. Now when you push the door to close it, you have so much friction or like so much mass you're trying to overcome that the door takes longer to get to its equilibrium point, or it doesn't even get there. Versus if it had just enough, like the Goldilocks of damping, such that it would just close on the first try. So, and that comes from the math here. You have cases where your omega is equal to 0, right? When this is equal to this, and that's critically damped. If you overdamp to an insane degree, then it would exactly. It would be impossible for the spring to get to equilibrium, correct? Which may be in this overdamped case. You see how this is like, this just like keeps going. Like I don't know if she's going to get there. And yeah, what happens is when you have something that's overdamped, right? Omega is the square root of a negative number, so omega becomes imaginary, right? And you'll learn about like imaginary frequencies when you do waves, which I guess we are doing waves, but even more so when you do quantum mechanics, you're going to deal a lot with like imaginary frequencies and like what those mean. Yeah. Okay, let's see. There might be some clicker question on things we've done already. Let me go check those real quick. Go see. Also, I'll give chat some time to ask some questions while I go through that. I know there's a little bit of a latency between me saying things and you guys responding, which is okay. Yeah, we're on ultra low latency. It should be the fastest. It should be critically damped latency. What's gonna be in your set this weekend? Probably some electro house. I love electro house. I'm a big fan. I like progressive too. It depends on like what. You have to read a crowd. It depends what the crowd's feeling. I have some like 140 like trap dubstep if people really want it. I don't know how wook Denver gets. When you mean by damping, is it like viscosity? Correct. Yes. So in the case here, right? Damping is any sort of force that is resisting the movement of this thing. So this thing naturally wants to go like back and forth because of the spring. But you can have stuff that's trying to impede that movement. In the case of the spring on a ground, that would be friction, right? Friction is what tries to impede the movement going back and forth. That's a damping. Here they're saying like the viscosity of the liquid creates like a drag force, and that's also damping. Hypothetically, if I attach myself on a large spring and jump off a high point, will I have a higher likelihood to survive when the system is underdamped, or am I just cooked either way? I think you'd have a higher likelihood of survival. Oh, I want to say if it's overdamped. Well, because I don't want you to hit the ground. The main thing that I guess like kills people is acceleration. Your organs don't like acceleration. Yeah. Your organs are cool with velocity, they're cool with position, but the second your organs start experiencing huge accelerations, such as, if you get into like a wreck or something, you have these you're in a car and you're moving and then suddenly you're not moving. Well, that had an acceleration because velocity changed. And the issue is that your organs want to keep moving, so they usually like rip themselves from your body, not to be like, morose and stuff, but yeah, so acceleration is the issue. So you want the thing with the least acceleration, which if for instance we were to look at our cases here, right? Acceleration is the slope of these graphs, right? So I feel like underdamped has the greatest slope, which is bad. Slope is acceleration, acceleration bad for body. So I think you want to be overdamped. Yeah, critically damped, you'd be cooked. I think underdamped, you'd be cooked the most, honestly. If we're talking about acceleration, yeah. Okay, cool. We do have some clicker questions. Let's go check those out. There we go. Okay, cool. So, the first question here, it says, a physical pendulum... Oh, wait, one sec. Google's talking to me. Okay, Google, stop. I have like one of those Google Homes, and sometimes it just listens to me and just starts speaking to me. And I'm like, excuse me? What else do you hear from me? I hope it doesn't hear like my Discord combos while I'm playing video games. Okay. So isn't bungee jumps underdamped due to their elasticity? They are, yeah. But I'm saying that like even a bungee jump like could kill you, right? If the change in well, let me think. Yeah, the interesting thing also, yeah, I guess also there's air resistance taken into effect too. That's another thing. Yeah. Yeah, ask me that during office hours. I'd love to go through that. Yeah, let's make sure we get the clicker questions done before we gotta head out. Okay, it says a physical pendulum starts from a position in which the center mass is directly above the suspension point. The pendulum swings past its equilibrium point with angular velocity omega. Neglect any friction. Find the period of small oscillations of the pendulum. Hint, it's described in the problem. Okay. So, okay, and then let me get the answer choices here. Okay. So, small oscillations. We remember from earlier in the class, right, that the period of small oscillations was equal to this, right? Omega was equal to the square root of mgl over I. mg L over I. And then, so period would be 2 pi, and then we flip this. And this would be I over mgl. Okay. Okay. Angular velocity omega. Find the period. Why? Okay, good question. Okay. So omega is equal to 2 pi f, right? And then f is equal to 1 over period. So period is equal to 1 over f, right? So here we would get that omega over 2 pi is equal to f. And then, so 2 pi over omega is equal to period, like if we were to flip it. Yeah. Okay. Directly above the suspension point. Oh, okay. Oh, I think I see what's happening here. Yeah. Sorry, I had to visualize this myself. Okay. Would we just skip to omega that? No, because here's the weird thing. Okay, so here, I'll show you what they're talking about here. They really should have included a picture on this. I had to see the solution and how they derived it, and then I was like, wait, where the fuck is this coming from? Okay, here's the key thing. It says the center of mass is directly above the suspension point, okay? So they're saying that your mass is starting up here, okay? And then I think they're saying that you're dropping it, okay? Once you drop it this way, then they're saying it's swinging back and forth. Yeah. Yeah. Okay. So yeah, we got to do conservation energy. This is mean. I don't like this question. I apologize. I saw this one and thought it was easy, and then I actually read it and I'm like, oh man, no. Oh. Okay, let's see. Okay, conservation of energy. So up here, let's call this. Let's call, for instance, this h equals 0. So then this is h is equal to 2L, right? If this is L, and then this is also L, and let's call this like the rotation point. Okay. So then energy before is just going to be mg times 2L, right? This is mgh. And then once the thing is down here and it is swinging, your potential energy due to gravity is 0, because your height is 0. But you do have rotational kinetic energy, which is equal to 1/2 I omega squared. Okay, I see what's happening here. Yeah, it's not 2 pi over omega. I'll show you why, Sophia. What? 1 sec. Okay. All right. So if we now solve for omega here, right? Let me see. Is anything going to cancel? Okay. I get omega squared is equal to 4. Four mgl, right? If I move that over, I get 4 mgl over I. And then let me see. Oh, okay. So should it be 2? 1 sec. Four mgl over I is that. Okay. And then for small oscillations, what is this small oscillation frequency they're talking about? One sec. I don't like this question. Yeah, I agree with this. Mg over I. 4 mgl over I is equal to omega squared. And then they say this, that T small is equal to, okay, is equal to 2 pi over this new omega, where that squared equals mgl over I, but that equals omega squared over 4. Is it? Yeah, well, that sucks. I don't like this. Wait. The pendulum swings past its equilibrium point. With a velocity omega. Okay. Yeah. Mastering physics is the worst, yeah. Okay. Yeah, whatever. I'm going to scrap this question. This is garbage. Because I can't even explain this. The correct answer for this one is 4 pi over omega. Let me take a look at this one over the weekend to see what they had. I'm still trying to understand it myself. But answer C. I don't like that question. Okay, we'll go C there. All right, this is a much better one. I thought that one was straightforward when I took a glance at it this morning. I was like, oh yeah, cool, yeah, whatever, we're good. But I'm still kind of understanding where they're getting the factor of 2 from. I don't get that. Okay, here, let's do this one. This one will make more sense. Okay, what is the length of a pendulum on Earth that has a period? Yeah, no diagram, just visualize. Exactly. Yeah, they didn't give me any diagram with that, so I'm kind of like, what the fuck is going on? I assume they're talking about it's up here and then it drops down, but then my problem with that is, isn't this thing gonna just like keep going back and forth? And that is not a small oscillation. That's very much not a small oscillation. That's a very large oscillation. Like, that's way more than 15 degrees. It's fucking 180 degrees, dog. Like, what? Okay. All right. Sorry. Enough ranting on that. Happy thoughts. Okay. This one we know, right? For a pendulum, this is equal to 2 pi square root of L over G, right? And so this is pretty straightforward. You just put this in your calculator. So I need period to be 15 seconds. And that's going to be whatever. We're going to figure out the length. And then G is 9.8. Cool. Solve. Man, this feels like some like good cop, bad cop situation, dude. Like what? This one's nice, but like what the hell was that other one? Okay. Square it. Times 9.8. Bingo. You get L is equal to 55.9. Wow. Okay, see, this restores my faith in like humanity. So this one should be answer choice B. Yeah, this is much better. Yeah, I like this. Yeah, happy thoughts. Okay, cool. And then good follow-up question. Which this is a key thing to know in physics, is how to look at equations and see what the relationships are with things, like how things will change. Okay. Okay. Let me get all the answer choices for you guys. No. Oh, it's the same thing. Yeah, okay, cool. Okay, so let's remember. So they say the period of a ball on a string if the balls are placed by a mass of 1/2 the mass. Okay. So let's remember our equation, right? T was equal to 2 pi square root of L over G. And we're talking about the ball having a different mass. Well, note here, right? Period does not depend on mass. Period stays the same. Yes. Should stay the same. Let's see. Let's make sure I have that as the right answer. No, I have it as D. Yeah. No, this should be period stays the same. I agree with this. Yep. This should be this. Yep. Yeah. Okay. Troubles in paradise today. Let me fix it. Oh, ball on a string. Oh, ball on a spring. Oh, thank you. Okay, I'm reading things all wrong today. Yes. Yes. Thank you. All right. One sec. Let me fix that. Sorry. I read this as a pendulum. I read this as ball on a spring. Ball on a string. Sorry. Okay. Fix. One sec. Yes. Okay. Ball on a spring. They should really say block on a spring. Bro, we don't have like balls on springs. Like what is this? Okay, fine. All right. For this, yes. Period is equal to 2 pi square root of m over k. Okay, cool. This makes sense. And then this one is a pendulum. This is period is equal to 2 pi square root of L over G. My bad. Yes. Okay, so this is correct. Okay, so this one does depend on the mass. Sorry, I read this as pendulum. Or I read this as ball on a string. It's ball on a spring. Okay. So in this case, period does depend on the mass. And so if the mass is halved, then this will go down by the square root of 1/2. Okay? If you didn't have the square root here, guys, and this went down by 1/2, then this would go down by 1/2. But because the square root is there, that decreases the effect of dropping it by 1/2, so such that it's the square root of 1/2. So if you put in your calculator square root of 1/2, now you would get 0.7 of what you used to have, or 0.71 of what you used to have. So yes, in that case, the period would decrease by 29%. And answer choice D is correct. Okay. Sorry, this is what happens when I'm worrying about missing my flight. Okay, let's do this one real quick, and then we'll end class. What happened to T equals 2 pi squared I over MGL equation? Does that depend on mass? That does, Asta, but with the pendulum, I is equal to ML squared, so the M and the I will cancel out the M on the bottom. Okay. The first question, I believe we should use the angular velocity. Oh, yeah, let's go over that one during office hours. I don't understand that one. Yes, okay. And then what will happen to the period of the pendulum if the same mass? This one should stay the same. Yes, this one should stay the same. Go to E. Okay, cool. So I was right. I'm just reading things wrong. Nice. Okay, cool. Okay, cool. I wanted to do driven oscillators, because driven oscillators are pretty cool too. But it's okay if we didn't have time for it. There's only so much I can do in an hour and, was it 15 minutes ago? Okay. Maybe we'll cover a little bit of that on Monday, like right before we get into the new stuff. Because forced oscillators are pretty cool. It's basically having like a damped oscillator, but then you also have like input force. So now you have two things fighting each other, right? You have something trying to stop the oscillations and something trying to increase the oscillations. And then they find some happy medium where they agree on a resonant frequency. And it's pretty cool. But we may go over that on Monday. If not, don't worry. I won't put it on the test. Yes, you do subtract that from 100 to get 29%. Yeah, so the reason for that, Amelia, right? Right, because being 0.71 is the same as decreasing by 29%. Yes. So like if I say 71% of the original, that's equal to like a 29% discount. Right? You guys ever go like clothes shopping at Zara or something and they're like, "Oh, everything's like 60% off," right? Well, 60% off means it's 40% the original price. That's how I would always do it, right? You know, instead of saying like, okay, but it's 20%, so take that off of the amount the total is, I would just be like, okay, cool. So what percentage of the original price is it? Okay, it's 40%. Cool. I just multiply by 0.4. Yeah. Anyways, okay, cool. All right. That's it for today's lecture.